All right. I guess it's 2:11. We can get started. So the reason I'm asking you to find where these intersect is because really the question I actually want to ask is, and we're going to find it, but we'll hold on for a second. We want to find the area between these two functions. And typically, if you're not told like between x equals 1 and x equals 7 or whatever some limits of integration are going to be, your first job is to find what those are by finding where the two functions intersect each other. So if we set these two things equal to each other, well, that pen does not show up very well. X squared minus 2x equal to 3x. I'm always bringing everything to one side, typically the side where you have the highest power being a positive coefficient. So x squared minus 2x minus 3x is minus 5x equal to 0. Factor out an x, and you're going to get x equal to 0 and x equal to 5. And you could find the y coordinates as well. If you plug in 5 for x here, you get 15. If you plug in 0 for x there, you get 0. So your actual coordinates are 0, 0, and 5, 15. You don't really necessarily need to know the y coordinates, but it doesn't hurt. So we'll talk about what this looks like first, and then we'll talk about how you do it without graphing it, because you definitely don't need to graph these two functions to figure out what the area between them is. Well, let's graph them anyway. So x squared minus 2x is an upward opening parabola. It's got an x-intercept at 0 and at positive 2, which let's make that kind of, we're going to go kind of big. And it looks something like, but not exactly like this. On the other hand, g of x equal to 3x is a straight line. It goes to the origin. Looks something like that. Wow, it's a straighter, like a line. Over here is your point, 5, comma, whatever. Over here is your point, 0, comma, 0. The idea with finding the area between these two curves is just like before, we're finding area under a curve, adding up a bunch of rectangles. So I like to draw a rectangle anywhere, specifically, I'm going to draw a rectangle right there. That rectangle, the area of that rectangle is the height times the width. The height of that rectangle is the top function minus the bottom function, which if I've graphed it is easy to see. The width of that rectangle is what? Well, it's a small change in x. I'm thinking of that small change in x as dx. Or if you like delta x, but I like dx. So that's the area of just one rectangle. That one there, or maybe this one over here, maybe this one over here. Right, and depending on where x is between 0 and 5, maybe the rectangle is really tall, maybe the rectangle is really short. So now if we want to find the total area, so I should say this area here is the area of a rectangle. Sorry, that's super tiny. If you want to find the total area, I'm going to, quote unquote, add up all the rectangles. But in calculus, how do we add up all the rectangles? We integrate. So we're going to add up all the rectangles from as far left as x equals 0 to as far right as x equals 5. The top function from my picture appears to be the straight line. The bottom function appears to be the parabola. If I hadn't drawn the picture, here's how you would figure it out. So these intersect at 0 and 5, meaning if I plug in 0 to either function, they should have the same y value. 0 minus 0 is 0, 0, 0. If I plug in 5 to either function, they should have the same y value. 25 minus 10 is 15. 3 times 5 is 15. So pick a point in between those two x values, like x equal to 1 or 2 or 4 or 3 or pick something easy. So if you pick, say, x equal to 1, g of 1 is 3 times 1, which is 3. f of 1 is 1 minus 2, which is -1. G of 1 is bigger. So that's the top. That's why g of x here is the top function, and f of x here is the bottom function. And we totally could have gotten this integral with these limits of integration without drawing this picture by just trying to figure out which one was on top by picking a point in between our intercepts there, our places where the functions intersect each other. The rest of this is stuff you already know how to do. Simplify the integrand. You're going to get 3x minus x squared plus 2x, so 5x minus x squared. Then anti-differentiate. You get 5x squared over 2 minus x cubed over 3 from 0 to 5. And we try not to worry too much about the math here. You get 5 times 25, which is 125 over 2, minus 5 times 5 times 5, which is also 125 over 3, minus 0 plus minus 0. I really don't want to add or subtract 125 halves minus 125 thirds. But I'm not so bad at subtracting 1/2 minus 1/3. And we can totally factor out 125 from both of these fractions, which is kind of a nice trick. And write this as 125 times 1/2 minus 1/3. 1/2 is 3/6, 1/3 is 2/6. Not a word I'm good at saying. And 125 minus or times 1/6 is going to be 125/6. You start picking fractions and have 6 on the bottom. So that is the general idea of how we find area between two curves. We find where they intersect, and then we find the integral of the top minus the bottom over the interval of integration. Let me ask you all something. When you have done this, I know most of you, a lot of you have already talked about this in class. Have all of your integrals been an integral where it was a function of x? Or has anyone talked about doing it in terms of y? Anyone y? Anyone y? Anyone y? Anyone y? Okay, I'm going to talk about it anyway, but we'll just do one example. Let's do one example because I'm going to show you why. No. Okay. I'm going to show you why. Sometimes it's better to do it in terms of y. And then we'll move on. So let's look at another example here. Unless you have questions about this one. Questions? Okay. So we might calculate. We'll start off with a setup. Oh, this actually brings up a good point. Sometimes on the test, someone will write the question as, set up this integral and do not calculate it. That means they just want you to write the integral and stop there. So make sure you read the questions carefully so you don't waste your time doing work that's not going to count for anything on the test. So be careful. Sometimes people like you to just set up, especially with volumes. A lot of times the question is just set up, but do not evaluate or do not integrate to find the actual number. So read those questions carefully. So let's set up integrals for the area between the following curves. Y equal to x squared, y equal to 1 over x, and y equal to 9. I don't have to worry about any other quadrants. No, in the first quadrant, yeah. In Q1. I will say, when you have more than 2 curves that you're dealing with, you really kind of have to draw a picture. Just 2 curves, you can set them equal to each other, find where they intersect. More than 2, you kind of have to draw it to see what's happening. So let's draw and see what's happening here. I know I'm limited to the first quadrant, so I'm not really going to worry about what's going on over here. Let's use some colors. Let's see if this pen actually works. Yeah, it works just fine. Okay. So here's y equals x squared in green. And then here's y equals 1 over x in blue. They intersect somewhere. I'm going to figure out what that is later. And then here's y equals 9 in red. And so I'm looking at this region right here. I wish I had like a pencil, but I don't. And I suppose I should find the points of intersection. So to find this point over here, where y equals 9 is intersecting y equals x squared, I'm going to set x squared equal to 9. And get x equal to plus or minus 3. But I know there it's positive 3. Over here it'd be negative 3. I'm not worried about that. And then I still have to find this point of intersection as well. If I set, so this is y equals 1 over x, set 1 over x equal to x squared. You guess I can multiply both sides by x. 1 equals x cubed, take the cube root. Cube root of 1 equals x, or x equals 1. So this is the point 1 comma 1. And finally up here, set 1 over x equal to 9. And I would just flip both sides. You get x equal to 1 over 9. Or if you want, you can multiply x and divide both sides by 9. That would also work just fine. But math is distracting. So now here's why it's terrible, in my opinion, to do this in terms of x, meaning in terms of top minus bottom. From x equals 1/9 to x equals 1, the top function is 9, the bottom function is 1 over x. So to find the area in this part of it, the area is going to equal the integral from 1/9 to 1 of the top function minus the bottom function. The top being y equals 9, the bottom being y equals 1 over x. But that's only this part here. I also have to add this part over here. And in that section over there, the top function is still 9, but the bottom function is now the green function, which is x squared. My limits of integration are from x equals 1 to x equals 3. Which we could totally solve. I don't really want to then. The point I want to make here is this is terrible, in quotes, because we had to use 2 integrals and we could have used 1. How could we have used 1? Well, let me draw the picture again really quickly. So we could have used 1 instead by, instead of drawing a vertical rectangle whose height is the top minus the bottom and whose width is dx, we could have drawn a horizontal rectangle where the height is the right minus the left function. And whose, right, that's my height right there. And my width is a small change in y, a dy. So we could also find the area of this region by integrating with respect to y instead of with respect to x. So the area could also be thought of as, sorry, plugging this point here. The integral from y equals 1 to y equals 9 of the right minus the left. But to do the right minus the left, I have to do things now in terms of y. So instead of this being y equals x squared, it's going to be x equal to the square root of y. Instead of y equal to 1 over x, if I solve for x, you're going to get 1 over y equal to x. That is a different way of writing an integral to calculate the same area. So most of the time when we do this, we got like to think of it as you're integrating or adding up rectangles from left to right. And then the area of the rectangle is the top minus the bottom times dx. But you can also switch your perspective and say, I'm going to integrate from y equals low to y equals high, or y equals bottom to y equals top. And then I'm adding up rectangles whose area is a height of right minus left times a width of dy. And if you calculate both of these, which I think is worth your time to do, you should get the same answer either way. It's kind of fun. But if none of your teachers have talked about this, you probably shouldn't spend much more time talking about it, because although it's valuable, it's not something you might or necessarily going to see. So let me ask again. Now that I've said this, does this doing it this way look familiar at all? And it's really okay if the answer is no. Now the answer is no. All right, that's okay. So let's do a couple more examples. The area is really kind of pretty straightforward in this way, in that you're just finding the area between two curves by doing the same process over and over again. Yeah, some things look uglier than others, but this idea is pretty much the same every time. Let's look at one or two more examples, and then we'll try and throw some word problems in there. I know it's always hard to get to things. So let's say I want to find the area between the curves. Oh yeah, I've got some good ones here. Y equal to, do I have some good ones? Yeah. 6 minus x, y equal to the square root of x, and sorry, let me think for a second. Yeah, and the y-axis, and x equals 0. And again, I got three things here, or more than two things, so I should probably just draw them. Fortunately, these are all curves that we are relatively familiar with. 6 minus x is a straight line. It's got a y-intercept of 6, an x-intercept of 6. I left my ruler in my office. That's disappointing. No, really disappointing. You're thinking that's a straight line. So there's my y equals 6 minus x. Square root function, usual look, something like that. And x equals 0 is the y-axis or the x-axis? Good question. Is it a vertical line or a horizontal line? Vertical. It's right here. There's x equals 0. So we're looking at this region here. Which I suppose, no, let's just be smart. Again, there's actually a reason why I'm talking about this drawing a vertical strip or horizontal strip for your area, because it really helps when we start talking about finding volumes using disks or washers, especially if you're revolving around. If you're only revolving around the x-axis, then you always want to use a vertical strip. But if you're ever revolving around the y-axis, then we typically need to use a horizontal strip. Unless someone's talking about shell method, which they're not supposed to in this class, but it doesn't mean they're not. So has anyone talked about shell method? Good. Let me know if anyone says shell method in your class, that they're other than saying we're not going to cover shell method. If they say we're going to talk about it, let me know, we'll talk about it. But usually it doesn't get covered in 17B, so we will not cover it unless we need to. So I'm going to use a vertical strip here. And to find the area, again, area is not terrible. Area is just the integral of the top minus the bottom. Ooh, what's the limits of, I need to find them. I'll figure out the limits of integration in a second here. So actually, let's figure them out now. So the left limit from our picture should be clear also from the fact that we were given x equals 0 as one of our lines, or one of our boundaries. That has to be our left limit of integration. But our right limit is essentially where these two functions intersect. Now, I would really prefer not to do the work of solving 6 minus x equal to the square root of x. Yeah, it's not hard, but it's work. Most of these problems are designed so that the points are relatively nice. And I shouldn't say caveat, most of these problems that are written by hand, not by web work, which none of you are using web work, so we're fine, are usually designed so that the points of intersection are relatively nice. So I might just start guessing square numbers, like x equal to 1. Nope, that doesn't work. 6 minus 1 is 5. Square root of 1 is 1. Or x equal to 4. 6 minus 4 is 2. Square root of 4 is 2. Oh, I scored. That's what I want. Most of the time, if you've got like a square root function in there or something that doesn't have very nice values all the time, you can easily guess what x is going to be. So that point there is 4, 2. And the x value is 4. So we're going as far left as x equals 0, as far right as x equals 4. Great. And then we're going to do the integral from 0 to 4 of the top function, which again, if we didn't have this picture, we could figure out by picking a number between 0 and 4 and plugging it in. Plug in 1. 6 minus 1 is 5. Square root of 1 is 1. 5 is bigger than 1. So the top function has to be the straight line. And I guess we should do this one. Let's actually finish it. So anti-differentiating the whole thing, we get 6x minus x squared over 2. The antiderivative of x to the 1/2 is going to be x to the 3/2 times 2/3. From 0 to 4. Okay, we plug in 4. We get 6 times 4 minus 4 squared over 2 minus 2/3 times 4 to the 3/2. We should be able to do minus 0 minus 0 minus 0. Let's see what we get. 24 minus 8. 2/3. 4 to the 3/2 is the square root of 4, right? That's the 1/2 power. 2 to the 3rd, which is 8. So we end up with 24 minus 8, 16 minus 16/3. And again, I don't really want to do 16 minus 16/3. I'm going to factor out a 16 because I can. Say this is 16 times 1 minus 1/3. I'm way better at 1 minus 1/3 than 16 minus 16/3. 1 minus 1/3 is 2/3. And 16 times 2/3 is 32/3. So if you happen to see things like that where you can factor out like a numerator and make your fractions less big to subtract from each other, I like to do that. I think it makes it easier personally. So area between, oh, we should do one more. We'll do one more. Do I have one more that I, nope, not you. No, we'll save that for later. We'll come back to that another day. Let's talk about one more area thing, and then I will, as promised, try to do some word problems here. Average value. Average value. I'm actually surprised that there's a whole section in your textbook dedicated to it, because the computation of average value is really not terrible. So to find the average value, average, can I spell it? Yes. Of a function over some interval, we calculate the following. You do the usual integral, so you find the area under the curve. And then you divide by the length of the interval. Which some people write like this, some people write like this. Whenever we minus a times the interval from a to b of f of x dx. So you're literally kind of saying how much area is under the curve and then dividing by the length to find the average height of the curve or the average value of the curve. So for example, find the average value of f of x equal to 3x squared on the interval from 1 to 3. And we'll draw a picture just because I think a picture is helpful. So this function looks kind of like this. And let's say here's 1, 2. It's kind of like you had a glass of water from 1 to 3, and you pour the water in, and the water is not going to stay like that. It's going to level out at some average height. Or as one student once told me, well, actually I should ask, does anyone here know what an ant farm is? The ant farm, it's the thing they used to have where kids would torture ants. They would put them, not really torture, but like you have like this plastic rectangle and you put like this little white kind of sand in it, and then you put ants in there and they would like make little tunnels and stuff. It was kind of neat. And then later they would die, but you know. Anyway, if you took the ant farm and shook up all the rocks and stuff, it would be some average height that would all be the same. The area hasn't changed, but the curve has gone from something like this to something that is totally level. That level height is the average value. So here, that's 3, 29, 27, sorry. To find the average value, we're going to find the integral from 1 to 3 of 3x squared. And then we're going to, let's actually write that as the area. That's equal to x cubed from 1 to 3, which is 27 minus 1, which is 26. That's the area, which is equal to the b minus a value times the average value. So this Sure, let's say it's about right there. This region here, this area in red, again, assuming my picture is, not terrible, should be the same as this area in blue. But the area in red is all at the same height, whereas the area in blue is the actual area under the curve. So our average value here equal to our integral from 1 to 3 of 3x squared divided by 3 minus 1, which is 26 over 2, which is 13. Which I know my picture is really not to scale. Sorry about that. So that's kind of the idea. If you took all that and just let it all lay even, that height it was all at would be the average value. Or in other words, the areas are the same whichever way you set it up. Whether it's the area under the curve or the area under this rectangle, it should be the same amount of area. Average value always kind of seems like, yeah, you just take this interval and then divide by how long the interval is. But it's more useful in the context of word problems. So let's look at a word problem or two. Let's see. So let's set this up. In some city, I don't know what city, the temperature in degrees Fahrenheit, T hours after 9 a.m. is modeled by the temperature at time t is equal to 50 degrees Fahrenheit plus 14 times sine of pi over 12 times t. Find the average temperature between 9 a.m. and 9 p.m. And before we do that, we're going to find the total temperature, which isn't going to make a whole lot of sense. We're going to find it. So the total temperature between 9 a.m. and 9 p.m. Okay, so at 9 a.m., what is my T value? It's not T equal to 9, because the way I'm setting this up, it says in some city, the temperature T hours after 9 a.m. So if I want actual 9 a.m., I should be setting T equal to 0, because I want 0 afters after 9 a.m. And then at 9 p.m., I should be setting T equal to what? 12 hours later. So I want to find the total temperature, again, which is a weird thing to say. Adding up a bunch of temperatures doesn't seem like a real normal calculation, but the total temperature would be equal to the integral from 0 to 12 of this temperature equation here. 50 plus 14 sine of pi over 12 t. Let's see what that gets us. So I'm just going to integrate. I'm going to get 50t. All right, sine. All right, sine. So when I integrate sine, I get negative cosine. So it's going to be negative 14 cosine of pi over 12 t divided by the coefficient of t, pi over 12. I know it's been a little while, but remember when you integrate something like cosine of 4x and you get sine of 4x divided by 4? Same idea here. We're getting cosine of something times t divided by that something. Evaluated from 0 to 12. So let's plug in 12. You get 50 times 12 minus, I should flip and multiply here. Let's say instead of 14 divided by pi over 12, it's 14 times 12 over pi. Cosine of pi over 12 times 12 is just cosine of pi. And we have to be extra observant here. We don't just get 0 if we plug in 0. So we actually need to be plugging in 0. If I plug in 0, I get 50 times 0 minus 14 times 12 over pi times cosine of 0, which is 1. So let's see. If I multiply this out, 50 times 12 is something. It's like 600. And then I get this, some gross numbers here. Cosine of pi is -1. So I'm going to get minus 14 times 12 over pi times -1. So plus 14 times 12 over pi plus, right, minus and minus is another. Oh, but it's a cosine of 0. That's a 1. Yeah, minus and minus. Another 14 times 12 over pi. Kind of gross. So the total temperature over these 12 hours is like, I don't know, more than 600 degrees. That doesn't make any sense, right? It's a weird thing to say because it's really 600 degrees times the unit of time, 600 degrees hours. So what we want to do, right, this is some number of degrees Fahrenheit times hours, which again, strange units. Because I want the average temperature, it's going to equal that integral from 0 to 12 of 50 plus 14 sine of pi over 12t dt divided by 12 minus 0. And now you've got units of degrees Fahrenheit times hours divided by hours. And the units will make sense. The hours will cancel and you'll just get a measurement in degrees Fahrenheit. And that's going to end up being that thing we got there divided by 12. So 1/12 times 600 plus, let's say we've got 2 of those, 2 times 14 over pi times 12. Sorry, I switched with the 14 and 12, but it doesn't really matter. And then dividing by 12, we end up getting 50 plus 28 over pi. Which is about 57 degrees, 58 degrees, 59 degrees. So that makes way more sense numerically. Right? If the temperature is a low of 50 in the morning and a high of I don't know what else in the evening, it seems reasonable that the average temperature would be 59 degrees, not like 600 degrees. The average temperature or the average of a function in general, someone says find the average of this thing over this interval, they're telling you to integrate and then divide by the length of time or the length of whatever has elapsed has elapsed. Okay. Let's look at a few more examples here. Yeah, sure. So oil leaks from a tank at a rate of e to the negative 2t gallons per minute. How much oil leaks in the first hour? So we're being told a rate of change, right? We're being told that oil is leaking at this many gallons per minute. And we're asking how much oil has leaked, meaning our end answer should be some number of gallons, right? Not gallons per minute, but just some volume of oil leakage. So typically, if you're given a rate of change and you're trying to find out just what the thing is, they're asking you to find an interval of this thing, right? If I know that oil leaks in gallons per minute, if I want to find the actual number of gallons that leak in the first hour, it's going to equal the integral from time equals 0 minutes to time equals 60 minutes, because, right, we were given things in measurement of minutes, not measurements of hours. E to the negative 2t dt. When you integrate a rate of change, you end up with the numerator, or essentially, when you integrate with respect to time, you're essentially multiplying by time. So like if I integrate someone moving at like 30 feet per second, and I integrate that, I end up with a measurement in feet because I'm essentially multiplying by a unit of time. So here, we end up with e to the negative 2t divided by negative 2 from 0 to 60 gallons. And then we would plug in, and the numbers are not nice here. We get e to the negative 120 divided by negative 2 minus e to the 0 divided by negative 2. I might simplify that a bit and write that as negative 1 over negative 2 is positive 1/2 minus 1 over 2 e to the 120. Not a very big oil spill here. I haven't even lost half a gallon yet. Not the point. So when you're integrating a rate of change, you end up with the numerical value of the thing that is changing. Another example of this would be something like, never enough room. If W prime of t equal to, I don't know, let's say something like, sure, 4 minus 1 over t squared represents the rate of growth in weight of a child in pounds per year. Again, my numbers are terrible here because I'm making stuff up. What does the integral from 5 to 10 of this represent? Well, W prime is measured in pounds per year. If we integrate from year 5 to year 10, we're going to get the weight. But it's actually the change in weight. So if we integrate this, we're going to get, we could actually integrate this. I'm going to write this long way first. The antiderivative of the derivative is just the function that you would have started with, which I know I'm not writing, from year 5 to year 10. So this would be the actual weight at year 10 minus the weight at year 5. Or in other words, the amount of weight gain from age 5 to age 10. Right, this is the weight at year 10. And I'm going to make up some numbers that don't correspond to this function because the function I picked here is not good with this example. But let's say that someone weighs, what does a 10-year-old weigh? 60 pounds, 70 pounds? No idea really at all. Let's pretend like a 10-year-old weighs something like 70 pounds and a 5-year-old weighs, I don't know. I'm really just making up numbers. 50 pounds? I really have no clue. Then you're saying that this integral represents the amount of weight gain, right? They ended year 10 at 70 pounds. They began year 5 at 50 pounds. This is how much weight they've gained over those 2 years, over those 5 years. And then you could also ask for the average weight gain by taking that integral and dividing it by what? Show me on your fingers. What would I have to divide this whole thing by to get the average weight gain? Yeah, exactly. I have to divide by 5 because that's how long my interval is. So the average change in weight or weight gain per year is going to be the same integral divided by the length of the time interval, which is in this made up situation here, 70 minus 50 pounds divided by, how did that 10 minus 5? Divided by 5, years. So that would be 20 divided by 5 is 4 pounds per year. Which again, probably not a very realistic number. It doesn't have to be realistic for the math to make sense. All right, let's see here. I know I had one. Yeah, no, not you. I feel like I've seen some of these. Yeah, these are always terrible. Survival and renewal problems. That sound somewhat familiar? Yeah. I don't believe, although I should ask your teacher, I don't believe this is an equation or a formula you need to memorize. I don't think you're expected to memorize it. You're supposed to be able to, like I do every time I'm asked to do these kinds of questions, look it up in a textbook or somewhere and then apply the formula correctly. But let's talk about what it all means. So survival and renewal. So yeah, let's say, suppose we start with a population of P naught. New members of the population are added at a rate of capital R of T. And the percent of the population that survives is, survives T years from now is given by the survival function S of T. So then R of T equals the renewal. S of T is the survival. And so we end up with the equation that P of T, the population at time T, and again, I don't think you need to memorize this formula whatsoever, unless your professor says otherwise, is S of capital T, which is different than little t, times P naught, plus the integral from 0 to capital T of S of capital T minus little t times R of little t dt. And let's talk about what things are. So, yeah. So this is, sorry. So what this represents is surviving from new members from time equals 0 to time equals capital T. That's what, oh, sorry, that's what this is here, all that. So this integral is all those of the new members that survive, and these folks right here are the ones who survive from the initial population. So that's the basic idea of this setup and why we're doing it this way. So basically, you're saying if we go from 0 to some later time, we're going to add up all those that survive from the new members that are added over that time. And then over here, you're just going to take your survival rate and then multiply by your initial population to figure out how many of those initial populations survived. Again, I don't really think a lot about this formula other than taking all the information and throwing it all into this formula, to be perfectly honest. Let's look at an example. I'll try not to get rid of this completely. So let's say we have the following situation. Can we see that? Maybe. Okay. Population of insects. Currently numbers. I think this is, I believe this is question number 3 from section 6.3, in case you're curious. Currently numbers 22,500 and is increasing at a rate of R of T equal to 1,225 times e to the 0.14 T insects per week. Okay. If the survival function is S of T equal to e to the negative 0.2 T, where T is measured in weeks, how many insects will there be after 12 weeks? All right. Yeah, and I knew I made it. Sorry. I feel like, let me just double check one thing here. Yeah, sorry. I made one tiny mistake. Remember this should have been a P of capital T. You're trying to find the population at a certain given time, typically. So let's identify all the things. Our capital T is 12. And our S of little t is e to the negative 0.2 t. And our R of t is 1,225 e to the 0.14 t. And our P naught is the initial population, which is 22,500. And honestly, I'm going to write the formula again because I don't remember. So I know that P of capital T is equal to S of capital T times P naught plus the integral from 0 to capital T of, I think this is the one that throws most people, the capital S of capital T minus T times R of T. And really, I'm just going to take everything and plug it into the things I have. So I'm finding P of 12. That's going to be equal to S of 12, which is e to the negative 0.2 times 12. I know these are not my favorite either. Times P naught, which is 22,500. Plus the integral from 0 to 12, S of T minus T. So I'm going to take my S function here, and where T exists, bless you, I'm going to write capital T, which is 12, minus lowercase t, which is lowercase t. So I'm going to get e to the negative 0.2 times 12 minus t. And then R of t is this 1,225 e to the 0.14 t. Which honestly looks pretty awful. It's not as bad as it looks. Let's see if we can wrap it up before we're out of time here, which we can definitely do. So this is not terrible. It's just e to the 2 times 12 is 24. So 0.2 times 12 is 2.4. So we're going to end up getting e to the negative 2.4 times 22,500, which I probably should have written first. Oh, well. Plus, let's simplify this a bit. Let's bring this 1225 out in front. And here's what I'd recommend. Break this up. E to the negative 0.2 times 12 is e to the negative 2.4. E to the negative 0.2 times negative t is e to the positive 0.2 t. And e to the 0.14 t is e to the 0.14 t. And this one that's a constant doesn't have to live inside the integral. That one can come right out. So let's do one more rewrite and then we'll finally integrate. We've got 22,500 divided by e to the positive 2.4, because that's probably how people are going to write it. Plus 1,225 divided by another e to the 2.4, because I'm bringing that one out as well. Right, let's just write it down there. There we go. And then finally, times the integral from 0 to 12 of e to the 0.36 t. That is not terrible. We know how to integrate e to the something times t. We're going to get, and I think I can make this fit, 22,500 over e to the 2.4. I should combine those. Those have the same denominator. 22,500 plus 1225 is 23,725. 23,725. Sorry, that's awful. I'm a terrible person. Oh, no, I shouldn't. I'm an idiot. Sorry, I'm not an idiot. I'm just making a dumb mistake. What am I doing? I'm forgetting that this is multiplied by that, and I'm trying to add these two things together. Wow, I should lose my license to teach. Not really, but I should be more careful. So what I should really have here is 22,500 divided by e to the 2.4 plus 1,225, sorry, divided by e to the 2.4. And then the integral of this is going to be e to the 0.36 t divided by 0.36 evaluated from 0 to 12. And finally, we're going to get 22,500 over e to the 2.4 plus gross numbers here, 1225. I bet 1225 divided by 0.36 turns out to be nice, but I'm not going to bother to find out right now. And then we're going to get e to the 0.36 times 12 minus e to the 0.36 times 0. And even though it's gross, not as terrible as it might seem. Usually, the hard part is making sure that you figured out what to plug in for T, for capital T, and really making sure that you deal with this part here appropriately. This is just this, which you really want to break up into these two constituent parts, so then you can put the T parts together and not worry about this part over here. And then integrating it is usually not too terrible. There's not a lot else to say about this problem other than that it's kind of gross, but maybe not as gross as you thought it would be. So, all right, that is all the time we have for today. On Wednesday, we can try to talk more about word problems, and we should probably also start talking about volumes of revolution.